All right, so let's just go ahead and use ordinary truth tables then with a couple of exercises from the text. And so we'll start first of all with this problem here, this statement. This is number 2 from the first set of exercises from 5.3. And so, as you see it here, G, horseshoe, G, horseshoe, G. And I'm sure after reading this problem, you're thinking to yourself, G. Anyway, just a little joke there. Glad I cannot hear the failure of anybody to laugh at it. But at any rate, continuing, we have just one letter here in this statement, and so we list all of the different letters in this statement off to the left, which of course is just the one, meaning that we have a 2-row truth table, true or false. For a statement this short, right, all of these shortcuts I've been talking to you about really take more effort than they're worth. I hope, recognize that it's this second horseshoe that is the main operator here, and so the order of operations will be those 2 G's feeding into the horseshoe, and then that horseshoe feeding into this one, along with the G from the right-hand side as well. And so, looking at true and false, true and false, true and false, just working our way across there. True, horseshoe, false, start over. True, horseshoe, true is true. False, horseshoe, false is actually true. We come to our main operator then. True, horseshoe, true is true. True, horseshoe, false is actually false, as we know. And so that's your ordinary truth table here. You want to go one step further, though, and say that this statement is contingent since it has some T's and some F's underneath the main operator column there, right? So you see that those single statements there in the first set of exercises from 5.3, and then you see in the second set pairs of statements where you do an ordinary truth table and then compare the main operator columns to determine if they're logically equivalent, contradictory, consistent, or inconsistent. But I want to turn next to actually the third set of exercises, which are actually word problems, right? Because people wonder, well, yeah, I can do an ordinary truth table, but how can it help me in my life? Is there any practical application to this material? Is a question that often gets asked in symbolic logic. And as we see here in the third set of exercises with these word problems, yes, there are, in fact, practical applications for ordinary truth tables. And to really drive that point home and to make that clear, I'll have you look at problem number 3 from that third set of exercises, in which we encounter a couple of individuals, Christina and Thomas, and they're having a discussion about their plans for the evening. And as the text writes here, or as it's written here, Christina says, "If you don't love me, then I'm certainly not going to have sex with you." Oh, okay, well, anyway. It's a fairly risque example here. This is as risque as the class will get. Nonetheless, Thomas responds, "Well, that means that if I do love you, then you will have sex with me, right?" Trying to sort of capture the tone of voice I imagine he would have, some sort of hint of desperation there. I don't know. But anyway, we'll leave that aside. The question, of course, is whether or not Thomas is correct. Thomas says that Christina's statement means the same thing as his statement, and though he may not realize it, what he's really suggesting there is that their 2 statements are logically equivalent, and that's how we can use an ordinary truth table to help out this particular couple here. And so, let me show you here. I've gone ahead and written this up here. You will see this on the first exam. I'll give you at least one word problem. What you'll need to do is translate the various statements you see in that problem, and I'll give you the letters to use, and I've done that here already. So what we find is Christina's statement here, and so maybe I'll indicate that. All right, so there's Christina's statement, and there's Thomas's statement. And so what Christina is saying is, if, right? She says if is the first word in her statement, so we have a horseshoe. So if, what? If you don't love me, and that's what tilde L is expressing, then I won't have sex with you. So this is Christina's statement here. Thomas's statement, he says, well, it means the same thing then to say if, so we have a horseshoe again, if I do love you, then you will have sex with me. So what we're going to do, and as I've already set it up here, we're going to do an ordinary truth table to see if these 2 statements actually end up meaning the same thing. And of course, before we get started on anything else here, as always, want to make sure we identify the main operator columns for these two statements. And so those two main operator columns look like this. And so we are now simply going to be able to plug in the L and the S values here. I'll just do it all the way across just to do it a little bit more efficiently. So we're looking at true, true, false, false for the L, and then the S here would be true, false, true, false. And then we go over here, we'll just go ahead and do the same thing for Thomas. True, true, false, false, and true, false, true, false. So let's remember that in terms of the order of operations, the L's will be feeding into the tilde here. This L will feed into the tilde, which then goes back and feeds into the horseshoe. And then that S value feeds into the tilde, which feeds into the horseshoe as well. So I know that's a little bit hard to read, but it's more so, I think, helpful if you can just see my hands do that order of operations. And then, of course, for Thomas, it's just the L and the S are feeding into the horseshoe. So that's fairly straightforward. So let's make sure we do all these tildes. And tildes, of course, just flip the values. So we're going false, false, true, true, and then the S. False, true, false, true, right? And so this is the critical thing, perhaps, in this whole problem, and that is to remember that it's the tildes, the tilde columns here, that are feeding in to the horseshoe. So we're looking at false, horseshoe, false. True, right? False, horseshoe, false is true. False, horseshoe, true. True. True, horseshoe, false. Well, that's the false one. And true, horseshoe, true is true. Coming over here, we get true, horseshoe, true is true. True, horseshoe, false is false. False, horseshoe, true is true. And false, horseshoe, false is also true. And so we finally come to the critical question here. Are they logically equivalent? They're the same, but they're different in the second row. And so these two statements, perhaps much to Thomas's chagrin, are not logically equivalent. Thomas is incorrect. That's the final answer there. You need to show all this work, of course, on the exam. You would need to always show all your work and show all of this, and then you would indicate that Thomas is incorrect. I mean, at the very least, he might be able to point out that the two statements are consistent. They are both true in at least one row, but I'm not sure what that means for their evening plans, and I will refuse to speculate. All right, so you have a couple other examples here of how to use ordinary truth tables to make a practical difference, perhaps, in your life.